The cosmos holds monsters that defy everything we know. In the darkness, there might exist a star so alien, it isn't made of atoms at all. It is called a strange star, a hypothetical cosmic object forged from a primordial soup of the universe's most fundamental particles. By the end of this, you will grasp a concept that reshapes the limits of matter itself. This is a journey to the very edge of known physics, where the rules break down and reality becomes fluid. We will explore how such a thing could form, why it might be the most stable substance in existence, and what its discovery would mean for our future. What does it feel like to stand at the precipice of a completely new understanding of the universe? To understand this cosmic oddity, we must first dismantle our most basic assumptions about what a star even is. Our sun, like countless others, is a massive sphere of plasma, a churning nuclear furnace where atoms fuse together under immense heat and pressure. When such a star dies in a supernova, its core can collapse into something far denser, a neutron star. Imagine the mass of our entire sun squeezed into a sphere the size of a city. In a neutron star, the gravitational crush is so absolute that electrons are forced into atomic nuclei, merging with protons to form a sea of neutrons. It is matter pushed to a breaking point, but it still has a structure. A strange star goes one catastrophic step further. The gravitational pressure inside a neutron star might, under the right conditions, become so overwhelmingly powerful that it shatters the neutrons themselves. These particles, which we once thought were fundamental, are not solid balls but are made of smaller things called quarks. The crushing weight breaks the bonds holding these quarks inside their neutron prisons, and they spill out, creating a vast, seamless ocean of free-floating quark matter. This is not a gas, a liquid, or a solid as we know them. It is a new state of existence, a quark-gluon plasma frozen into a super-dense, super-stable soup. And in this particular recipe, the soup is made with 3 equal ingredients: up quarks, down quarks, and the more exotic strange quark. This is strange matter. A strange star, then, is not a ball of fire or a crystal of neutrons. It is a single, gargantuan droplet of this primordial quark soup, held together by its own unimaginable gravity, a perfect and perhaps indestructible sphere of the universe's most basic ingredients. But to grasp why this strange matter is so stable, we need to meet the ingredients. Deep inside every atom in your body, holding everything together, are particles so small they have no internal structure at all. These are quarks. Think of them as the absolute Lego bricks of reality. In the calm, ordinary world we live in, quarks are never found alone. They are always bound in groups of 2 or 3 by a force so powerful it actually grows stronger the farther you try to pull them apart. This is the strong nuclear force, the cosmic glue that holds the nucleus of every atom together. The most familiar quarks are named, quite simply, up and down. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up. Every single thing you have ever touched, every star you have ever seen, is built from different combinations of just these 2 particles. They are the reliable workhorses of the universe. Then there is the strange quark. It is a heavier, more exotic sibling to the down quark. In particle physics, it carries a property called strangeness, a whimsical name for a very real quantum characteristic that makes it behave differently. Under normal conditions, a strange quark is unstable and will quickly decay into its lighter cousins, but normal conditions are not what we are talking about here. Inside the crushing heart of a dying neutron star, the rules of the game change completely. The pressure is so astronomically high that the space between particles vanishes. In this environment, it actually requires less energy for a down quark to transform into a strange quark than it does for it to remain a down quark. It is like a crowded room where standing on a stool takes up less space than trying to stand normally. So, one by one, the down quarks in the neutron soup convert. The result is a perfectly balanced mixture of up, down, and strange quarks, all floating freely in that dense ocean. This trio, in this specific ratio, achieves a state of perfect energetic harmony. Physicists call this the true ground state of matter. It means that this strange quark matter could be the most stable form of matter in the entire universe, more stable than the iron in a skyscraper or the diamond in a ring. A strange star, therefore, would not be some fragile, exotic anomaly. It might be the universe's ultimate endpoint for matter, a perfect and permanent crystal of reality's most basic ingredients. This perfect stability creates a star through a process of unimaginable violence. The birth of a strange star begins not with a whisper, but with the loudest explosion in the cosmos. A massive star, many times heavier than our Sun, reaches the end of its life. For millions of years, it has fused elements in its core, building up a layered structure like a cosmic onion. When it finally creates a core of iron, the fusion process no longer releases energy, it consumes it. The star's internal furnace abruptly shuts off. Without the outward push of radiation, gravity wins in an instant. The core collapses at nearly a quarter the speed of light. The outer layers of the star, now unsupported, crash inward and then rebound in a cataclysmic shockwave we call a supernova, outshining entire galaxies. What remains is the star's dense, collapsed heart. If this remnant core is below a specific mass, known as the Tolman-Oppenheimer-Volkoff limit, it settles as a neutron star. The inward crush of gravity is held at bay by a bizarre quantum rule called neutron degeneracy pressure, which essentially states that neutrons refuse to be squeezed into the same space. But if the core is above that critical line, the story takes a darker turn. The gravitational force becomes too powerful for even quantum rules to resist. The degeneracy pressure fails, the collapse does not stop. The core continues to implode, and the pressure soars to levels that make a neutron star seem spacious. It is here, in this final, ultimate squeeze, that neutrons themselves are shattered. Imagine taking a walnut and crushing it in a hydraulic press until the shell vanishes, and you are left with only the fragmented meat inside. The neutrons, each a tiny bag holding 3 quarks, are ruptured. Their constituent quarks, the up and down quarks, are set free. For a fleeting moment, the core becomes a seething, primordial soup of quarks and the gluons that mediate the force between them, a state of matter not seen since the first microseconds after the Big Bang. This quark-gluon plasma is unimaginably hot and chaotic, but in the dense, pressurized environment of the collapsing core, it rapidly cools and finds a new, lower energy arrangement. The liberated down quarks, seeking stability, readily transform into strange quarks. The entire core crystallizes not into atoms, but into that perfectly balanced mixture of up, down, and strange quarks. The collapse halts. A new object is born from the ashes, not a neutron star, but a single, city-sized droplet of strange matter, a strange star. It is a phoenix forged from the complete destruction of atomic structure, a perfect sphere of the universe's most fundamental recipe. This perfect, stable droplet of quarks would possess properties so extreme they border on magic. If the Bodmer-Witten hypothesis is correct, a lump of this strange matter would be more stable than the most stable atomic nucleus we know, which is iron 56. Think of iron as the ultimate endpoint of stellar fusion, the ash left in the furnace of a star. It represents the pinnacle of stability in the atomic world. But strange matter proposes something radical, that beneath the level of atoms, there exists an even more fundamental and unshakable state. A single gram of this quark matter, if it could be created and kept stable outside the crushing core of a star, would theoretically never decay. It would be a permanent, indestructible speck of the early universe, frozen in time. But the strangeness does not stop with mere stability. The internal behavior of this quark soup is where physics truly becomes surreal. Within that super-dense droplet, the quarks are not locked in place. They are theorized to flow with almost no resistance whatsoever. This near-perfect fluidity, a state with virtually zero viscosity, means the interior of a strange star could behave like a single, frictionless superfluid. If you could stir it, the motion might never stop. This is not just a liquid, it is the ultimate liquid, a substance where turbulence vanishes and flow is perpetual. Furthermore, this quark sea would likely be a superconductor, but not of electricity as we typically understand it. It would be a color superconductor. Remember, the force that binds quarks is called the strong force, and it carries a charge known as color, a fanciful name for a property unrelated to visible light. In this bizarre environment, the quarks could pair up in ways that allow the color charge to flow without any resistance. The entire star would conduct this fundamental force perfectly. It is a concept that defies everyday analogy, a kind of hyper-efficiency at the quantum level that makes our best superconductors seem clumsy and slow. So picture the totality of this object, a city-sized sphere heavier than our sun, that is simultaneously a superfluid, a color superconductor, and a perfectly stable crystal of deconstructed reality. Its surface, if it even has a distinct one, would be a boundary sharper than any razor, where the density plunges from 1 billion tons per teaspoon to the near emptiness of space in a span of maybe a single millimeter. It would not twinkle or have sunspots. It would be a dark, almost perfectly smooth orb, possibly cloaked in a thin crust of ordinary neutron star matter, radiating heat left over from its violent birth. It is an object of terrifying perfection, a cosmic artifact so efficient and stable that it makes every other form of matter in the universe seem temporary and flawed by comparison. But theoretical perfection is invisible from Earth. Our only way to find such a star is to search the sky for something that does not fit. In the constellation Corona Australis, about 400 light-years away, astronomers found an object that refused to follow the rules. It is a neutron star candidate known as RxJ 185653754. For years, it was simply another faint, spinning stellar corpse, a pulsar emitting X-rays into the void. Then, in the early 2000s, the newly launched Chandra X-ray Observatory turned its powerful gaze toward it. What Chandra saw sent a ripple of excitement through the astrophysics community. By analyzing the spectrum and intensity of the X-rays coming from its hot surface, scientists could estimate its size. The calculations pointed to a radius of only about 6 kilometers. This was a serious problem. According to the most robust models of neutron star physics, a neutron star of its estimated mass simply could not be that small. The equations of state, which describe how matter behaves under such extreme pressure, would not allow it to be so compact. It was like finding a suitcase that, based on its weight, should be full of lead but was somehow the size of a lunchbox. The density implied by those measurements was staggering, pushing beyond what a soup of neutrons alone could withstand. The only plausible explanation for a thrilling moment was that this object was not made of neutrons at all. It had to be made of something even denser, something that could pack the same mass into a tighter, smaller volume. That something was quark matter. RxJ 185653754 became the first serious observed candidate for a strange star. The idea that we might have actually found one, a single perfect droplet of primordial quark soup floating in our galactic neighborhood, was electrifying. It was no longer just a scribble on a theorist's chalkboard. It was a real point of light in the data, challenging our fundamental understanding of matter. The detective work, however, had only just begun. In science, a single anomalous measurement is a clue, not a conviction. Later observations, particularly with XMM Newton, another space-based X-ray observatory, collected more data. As analysis techniques grew more sophisticated, a different interpretation emerged. the star's X-ray emission might be coming not from its entire surface but from hotspots near its magnetic poles. If that were the case, the estimated size could be an illusion, a trick of perspective and temperature. Revised models suggested a more conventional neutron star radius, one that fit comfortably within the known equations of state. The strange star hypothesis, while not ruled out, lost its most compelling piece of evidence. Yet the candidate status remains. This back and forth is not a failure of science, it is the very engine of discovery. It perfectly illustrates the meticulous, often frustrating detective work of astrophysics. We are forensic scientists examining a crime scene 400 light-years away, with only the faintest whispers of light as our evidence. A measurement contradicts a model, so we question the measurement. A new model explains the data, so we question the model. RxJ 1856.53754 taught us that the signature of a strange star is subtle, hiding in the precise details of radiation we can barely detect. It shifted the search from simply finding small, dense objects to looking for more specific, stranger signals. The hunt is now for a star that does not just bend the rules, but shatters them in a way no neutron star ever could. The search for a strange star now listens for the sound of a star breaking its own bones. Across the galaxy, many neutron stars reveal themselves as pulsars, cosmic lighthouses that sweep beams of radiation past Earth with metronome-like precision. Their spin rates are astonishingly regular, but they are not perfect. Occasionally, one of these celestial clocks will suddenly, inexplicably tick faster. In a fraction of a second, its rotation speeds up by a tiny but measurable amount before settling back into a gradual slowdown. Astronomers call these events glitches. For decades, the leading explanation has been a starquake. Picture a neutron star's crust, a crystalline lattice of iron nuclei 100 trillion times stronger than steel. This crust is rigidly locked to the superfluid neutron ocean swirling beneath it. As the star's powerful magnetic field breaks its rotation, the crust slows down. The fluid interior, however, can keep spinning faster. This creates an immense strain, like twisting a spoon in a jar of honey until the honey grips it tight. Eventually, the stress becomes too great. The entire crust fractures and shifts, snapping into a slightly more compact shape. Just as a spinning ice skater pulls their arms in to accelerate, the star's sudden contraction causes its rotation to jump. This is the neutron star glitch, a seismic event on a sphere of unimaginable density. But what if the object experiencing the glitch is not a neutron star at all? What if it is a strange star? The internal architecture would be fundamentally different. Instead of a superfluid neutron ocean, the core is that frictionless quark soup. And its surface might be capped not by a thick iron crust, but by an incredibly thin, incredibly dense shell of normal matter, perhaps only centimeters thick, held down by the star's ferocious gravity. This changes the physics of a starquake completely. The cracking of a thin, ultra-dense crust on top of a perfectly fluid interior would release energy in a different way. The patterns of the glitch, its size, its frequency, and how the star recovers afterward would carry a unique fingerprint. A strange star might exhibit more frequent, smaller glitches as its brittle skin constantly adjusts. Or its glitches might be far more violent and rare, as strain builds for centuries before the entire shell shatters at once. Some theorists even suggest that a pure strange star with no crust at all could not glitch in this way, its fluid surface having nothing to crack. This turns a puzzling astronomical phenomenon into a potential decoder ring. By meticulously cataloging the glitches of thousands of pulsars, astronomers are looking for the outlier, the star whose hiccups simply do not fit the established models of neutron star quakes. Finding one with a glitch signature that only a strange quark core could produce would be a monumental discovery. It would be like listening to a vast orchestra of identical drums and suddenly hearing one that rings with the clear, pure tone of a bell. That singular, aberrant signal could be our first true whisper from an object made not of atoms, but of the universe's primordial ingredients. That thin, brittle crust is itself a subject of fierce debate. The surface of a strange star is a frontier where known physics meets pure speculation. On one side of this scientific argument, theorists propose a star with a skin. This model suggests the quark ocean does not touch the vacuum of space directly. Instead, a thin layer of normal matter, perhaps only a few centimeters thick, floats above it. This crust would be made of incredibly dense ionized atoms, likely iron or something even heavier, stripped of their electrons. It is held aloft not by solid ground, but by a powerful electric field generated by the quark matter itself. Think of it like a sheet of metal hovering over a powerful magnet. The quarks below create a positive charge which repels the positively charged atomic nuclei in the crust, preventing them from sinking. This delicate balance creates a surface we might recognize, a solid boundary from which starquakes could originate and thermal radiation could escape in a more familiar pattern. The other model is far more radical. It argues for a star with no skin at all. In this scenario, the quark matter reaches right up to the edge. The star has a bare quark surface, a perfect, mathematically sharp boundary where the densest substance in the universe meets the absolute nothingness of space. There is no cushion, no intervening layer. This surface would be unlike anything we have ever conceived. It would be perfectly smooth at an atomic level, a flawless curve with no mountains, no valleys, not even a speck of dust. The transition from 1 billion tons per teaspoon to pure vacuum would occur over a distance smaller than a single proton. This choice of models is not just academic. It dictates everything about how we could detect such an object. A star with a crust would have starquakes as that rigid skin cracks under strain. Its thermal emissions, the X-rays and gamma rays leaking from its surface, would come from this hot solid layer, giving us a specific signature to look for. Its interaction with its own intense magnetic field, its magnetosphere, would be channeled through this crust, potentially creating pulsar beams similar to neutron stars. A bare quark star, however, would be silent in a seismic sense. With nothing solid to crack, it could not have starquakes in the traditional way. Its heat would radiate directly from the quark sea, which might produce a very different, much smoother spectrum of light. And its magnetosphere would be anchored directly into that superconducting quark fluid, possibly generating magnetic fields of unimaginable complexity and strength, fields that could twist and reconnect in ways that produce bursts of energy we have never seen. This is the critical puzzle for future telescopes and gravitational wave observatories. They will not just be looking for a dense object, they will be listening for the subtle language of its surface. Does the data whisper of shattering crystal or the perfect, silent sheen of a primordial droplet? The answer will tell us if the universe allows perfection to wear a mask or if it stands utterly naked against the dark. This perfect stability leads to a startling and controversial possibility. If strange matter is truly the most stable state, then any chunk of it, no matter how small, should also be stable. Physicists call these hypothetical fragments strangulets. Think of them as cosmic seeds, tiny droplets of that primordial quark soup, potentially no larger than a grain of sand but with the density of an entire mountain. They would be indestructible, permanent, and incredibly dangerous. How could such a thing come to exist outside the heart of a strange star? The answer lies in another cataclysmic event. When two strange stars, locked in a gravitational dance, finally spiral together and collide, the impact is beyond comprehension. The merger would rip open their perfect quark surfaces, hurling fragments of this exotic substance out into the galaxy at incredible speeds. These ejected fragments, cooled and stabilized, would become strangelets, wandering the interstellar void like bullets made of a new phase of reality. This raises a profound and unsettling question. For decades, physicists studying cosmic rays, the high-energy particles raining down on Earth from space, have detected anomalies. Occasionally, they find particles with such extreme energy and unusual characteristics that they defy easy explanation. One controversial proposal is that some of these ultra-high energy cosmic rays are not protons or atomic nuclei at all. They could be strangelets, a single charged strangelet accelerated by the magnetic fields of a supernova or a merging black hole could streak across the galaxy and slam into our atmosphere. Its impact would be unlike anything from a normal particle. The real fear, however, is not the impact itself, but what might happen next. This is the core of the strangelet doomsday hypothesis. If a stable strangelet were to strike a planet like Earth, it could theoretically begin converting the normal atomic matter it touches into more strange matter. The process is akin to ice crystallizing in supercooled water. The strangelet acts as a seed. Upon contact, the immense density and stability of its quark structure could cause the protons and neutrons in nearby atomic nuclei to dissolve, their quarks reassembling into the more stable up-down strange configuration. This would release energy and create more strange matter, which would then convert the matter next to it. In a hypothetical chain reaction, the entire planet could be transformed, atom by atom, into a giant cold lump of strange quark matter. It sounds like science fiction, but it is a scenario taken seriously enough to be studied. Before starting up the Large Hadron Collider, the world's most powerful particle accelerator, scientists conducted rigorous safety reviews. One question they had to answer was whether the high-energy collisions could, under any conceivable condition, create a microscopic strangelet that could then begin this catastrophic conversion. The consensus after extensive analysis was a firm no. The conditions in the collider are fundamentally different from those inside a collapsing stellar core. The energy densities, while immense, are fleeting and minuscule in volume compared to a star. Furthermore, if strangelets were so easy to create and so stable, we would likely see evidence of them everywhere in the universe, and we do not. The cosmos, with its constant, far more violent collisions, would have already seeded the galaxy with them. Yet the mystery persists. The search for strangelets continues in cosmic ray data and in the debris of heavy ion collision experiments. They remain a shadowy possibility, a reminder that the universe may hold ingredients we do not fully understand, and that the line between a wondrous discovery and a fundamental threat can be incredibly thin. To grasp the density of a strange star, we must first reset our intuition entirely. The world we inhabit is built on a foundation of emptiness. Every atom is a miniature solar system with a dense nucleus at the center and electrons whizzing around in a vast, empty void. If you could remove all the empty space from the atoms in every human being on Earth, the entire human race would fit into a single sugar cube. That cube would weigh billions of tons. This is the first clue to the bizarre nature of compacted matter. Now, let us compress things further. Take a familiar starting point. A cubic centimeter of water, a little sugar cube's worth, has a density of 1 gram per cubic centimeter. That is our baseline. The iron in a car engine is about 8 times denser. The core of our sun, under immense pressure, reaches about 150 grams per cubic centimeter. These are numbers we can almost comprehend. Then we cross into the realm of the stellar dead. A white dwarf, the Earth-sized core of a sun-like star, has a density of about 1 million grams per cubic centimeter. A single teaspoon of its material would weigh as much as an elephant. This is staggering, but it is merely the prelude. A neutron star is where physics truly warps. In its interior, atomic structure is annihilated. Nuclei are gone, electrons are gone. It is a sea of neutrons packed shoulder to shoulder. The density soars to approximately 10 to the 14th power grams per cubic centimeter. That is 1 followed by 14 zeros. A single teaspoon of neutron star material would weigh not like an elephant, but like every single person alive today, all 10 billion of us compressed into a single tiny spoonful. The weight of all humanity in a teaspoon, this is the frontier of known matter, and now we step beyond. A strange star, a single droplet of pure quark matter, is denser still. Theoretical models suggest it could be anywhere from 10 to 100 times denser than a neutron star. Let us take the conservative estimate, just 10 times. That pushes the density to 10 to the 15th power grams per cubic centimeter. A single teaspoon of this strange matter would no longer weigh as much as all living humanity. It would weigh as much as every human who has ever lived across all of history, perhaps 100 billion souls, all their mass crushed into that one metallic spoon. If we push to the extreme end of possibility, the numbers become pure abstraction. The entire mass of Mount Everest, over 160 trillion kilograms of rock and ice, could be compressed into the volume of a single sugar cube. This is not merely heavy. This is a fundamental reordering of reality. At these densities, the very idea of separate particles begins to blur. The quarks are not little balls in a jar. They are a continuous, seamless fluid, a new phase of existence where matter has been compressed to its absolute mathematical limit. To hold such a substance is an impossibility, for it would instantly tear through any container and plunge through the Earth like a ghost through a wall, drawn relentlessly toward the planet's core by its own unimaginable gravity. This density is not just a statistic, it is the signature of a universe operating on rules we are only beginning to decipher. Deep within that perfect quark ocean, another layer of magic unfolds. The quarks do not simply float in a dense soup. They may organize themselves into an even more exotic state called a color superconductor. To grasp this, think of a regular electrical superconductor here on Earth. At extremely low temperatures, electrons overcome their natural repulsion and pair up, forming what are known as Cooper pairs. These paired electrons can then flow through a material without any resistance whatsoever, creating a perpetual current. This is the secret behind floating maglev trains and incredibly powerful magnets. Inside a strange star, a similar pairing happens, but the scale and the force involved are on a completely different level. Here, it is not electrons pairing via the electromagnetic force. It is quarks pairing via the strong nuclear force, the most powerful fundamental force in the universe. This is color superconductivity, and the name color refers not to light, but to the whimsical label physicists gave to the charge that quarks carry for the strong force. In this bizarre environment, quarks of different types, flavors, and colors link together in coordinated dances. The most symmetric and stable configuration theorists have proposed is called the color flavor locked phase. In this state, the quark's color charge and its flavor identity, whether it is up, down, or strange, become inextricably linked. It is as if every quark's personal identity is fused with its role in the cosmic dance, creating a perfectly synchronized, rigid order throughout the entire star. This is not a fluid with some special properties. It is a single, coherent quantum object the size of a city. The implications of this internal order are profound. First, it dramatically changes how the star cools. A newborn neutron star radiates away its ferocious heat primarily by emitting neutrinos, ghostly particles that barely interact with matter. In a color superconductor, however, the paired quarks have a harder time losing energy. The formation of this orderly state actually releases a burst of neutrinos, but afterward, the star's cooling could slow to a crawl. A mature strange star might be significantly colder than a neutron star of the same age, a potential fingerprint we could detect with sensitive infrared and X-ray telescopes. Second, it dictates the life and death of magnetic fields. In an ordinary star, magnetic fields are generated and sustained by churning, electrically conductive fluids, a process called dynamo action. But in a color superconductor, magnetic fields behave in a stranger way. they might not permeate the entire star. Instead, the superconducting quark fluid could expel an external magnetic field, a phenomenon known as the Meissner effect, confining it to thin, incredibly intense vortices or a shallow surface layer. Alternatively, some theories suggest the star could generate its own, self-sustaining magnetic fields frozen into the superconducting matrix from its violent birth. These fields would be unimaginably strong and stable, potentially surviving for billions of years without decay. Finally, this internal superconductivity is the ultimate source of the star's legendary stability. The paired quarks in the color-flavor locked phase have achieved the absolute lowest energy state permitted by the laws of quantum chromodynamics. It is the universe's most comfortable chair for matter. Any attempt to disrupt this arrangement, to heat it up or tear it apart, would require an astronomical input of energy. This is why a strange star is not just dense, it is cosmically robust, potentially surviving collisions and mergers that would shatter a neutron star. The physics here is at the bleeding edge of our understanding, a tapestry woven from quantum theory and extreme gravity. It suggests that the most stable object in the cosmos is not a silent, dead rock, but a dynamic, quantum-ordered crystal, humming with locked-in perfection at the heart of the dark. The silence of a strange star hides a violent potential. When these perfect spheres of quark matter are not alone, their existence may be revealed not by light, but by the shudders they send through the fabric of reality itself. This is the domain of gravitational wave astronomy, a new way of listening to the cosmos. Every massive object that accelerates creates ripples in space-time, like a boat moving through water. But the waves are unimaginably tiny, detectable only from the most cataclysmic events, like the collision of black holes or neutron stars. In 2015, the LIGO Observatory made history by hearing the first direct chirp of two black holes merging, a discovery that confirmed a century-old prediction by Einstein. This opened a new window on the universe, one that does not rely on light. It listens to gravity itself. Now, scientists are tuning their ears to an even subtler symphony, hoping to catch the unique note of quark matter. When two compact objects spiral together, their immense gravity pulls on each other, stretching and squeezing them long before they touch. These tidal forces deform the stars, and the way an object deforms depends entirely on what it is made of. A neutron star has some give, a slight squishiness governed by the complex nuclear forces holding its neutrons together. Its deformation leaves a specific imprint on the gravitational wave signal in the final moments before collision. A strange star, however, would be fundamentally different. That perfect, frictionless quark ocean, possibly topped with an ultra-thin, brittle crust, would respond to tidal forces in a unique way. Because its internal pressure comes from the degeneracy of free quarks rather than nuclear interactions, it could be far more resistant to deformation. A strange star might be almost incompressible, behaving more like a rigid ball bearing than a soft grape. If two strange stars were to merge, the gravitational wave signal would carry the signature of that incredible stiffness. The in-spiral chirp would be cleaner, with less of the tidal distortion we expect from neutron stars. Alternatively, if a strange star with a thin crust merged with a neutron star, the moment of first contact would be spectacularly violent. The neutron star's matter, upon touching the quark surface, could be instantly converted into strange matter, releasing a flash of energy and altering the merger dynamics in a way that would ring through space-time. Future observatories are being designed to catch these nuances. Ground-based detectors like LIGO and Virgo are excellent for hearing the final high-frequency mergers. But to hear the longer, lower-frequency song of two objects spiraling for months or years before they collide, we need to go to space. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart. It will listen for the gravitational hum of supermassive black holes and the steady drone of countless binary systems, including pairs of strange stars long before they merge. Even further ahead, projects like the Einstein telescope, a next-generation underground observatory, promise sensitivity so great it could detect the faintest tremors from individual pulsar glitches or the quark matter oscillations inside a newly born strange star. These instruments will not just hear collisions, they will perform cosmic autopsies, deciphering the interior composition of the dead stars from the ripples they create in their final moments. The dream is to one day catch a signal that defies all models of neutron star mergers, a chirp that can only be explained by the presence of that perfect, unyielding quark matter. It would be a whisper from the dawn of time, written not in light but in the bending of space itself. The most powerful magnets in the universe are not on Earth. They are the corpses of stars called magnetars, neutron stars with magnetic fields so intense they could strip the information from every credit card on our planet from halfway across the galaxy. These fields are a quadrillion times stronger than Earth's, and they power violent, star-shattering outbursts of X-rays and gamma rays. But what if the engine behind these magnetic monsters is not a neutron star at all? The unique physics of strange matter could turn a strange star into the ultimate cosmic dynamo, forging magnetic fields of truly incomprehensible power. To understand why, we need to look inside a collapsing star core. During the supernova that births either a neutron star or a strange star, the progenitor star's own magnetic field is not destroyed. It is trapped, compressed, and amplified as the core shrinks from a sphere the size of Earth to a city. This process, called flux conservation, is like a skater pulling their arms in to spin faster but for magnetic field lines. The field becomes unimaginably dense. In a normal neutron star, this initial field is then shaped by the churning, electrically conductive soup of neutrons and protons in its interior. But the interior of a forming strange star is a different beast entirely. It starts as that hot, chaotic quark gluon plasma, a perfect conductor, and then rapidly crystallizes into a color superconductor. This phase change is a critical moment. As the quark matter cools and the quarks pair up into that locked, orderly state, the magnetic field lines threading the fluid could be frozen in place, trapped within the superconducting matrix like flies in amber. This process could preserve magnetic field strengths far beyond what a neutron star's more turbulent interior could sustain. Furthermore, the fluidity of the quark sea allows for dynamo action on a scale and efficiency neutron matter cannot match. A dynamo requires motion in a conductive fluid. In a newborn strange star, the core is not a placid lake. It is born spinning, potentially at hundreds of times per second, and it is seething with convection as it cools. This spinning, convecting, perfectly conductive quark fluid is a recipe for amplifying magnetic fields to ludicrous extremes. Think of it as the difference between stirring water and stirring molten iron. The iron, being a better conductor, can generate and hold a much stronger magnetic field from the same motion. The strange quark ocean is the ultimate molten iron. Some models suggest that in the first few seconds after its birth, a strange star's internal dynamo could ramp up magnetic fields to levels 1,000 times stronger than those of the most powerful known magnetars. We are talking about fields so strong they begin to distort the quantum vacuum of space itself, a realm where physics becomes speculative and wild. This leads to a compelling and testable idea. What if the magnetars we have already catalogued in our galaxy are not all neutron stars? Some of them, particularly the most extreme and unstable ones, could be strange magnetars. Their observed behavior might be the key clue. Neutron star magnetars are known for sudden, gigantic X-ray flares and slower, steady pulsations. But a strange magnetar with its different internal structure could behave in even more dramatic ways. That thin, brittle crust theorized to cap some strange stars would be under tremendous strain from the insane magnetic field frozen beneath it. The crust could shatter more frequently and more violently, producing not just glitches but colossal starquakes that rip open the star's surface. Each quake would release a flood of trapped magnetic energy, resulting in an outburst far more energetic than a typical magnetar flare. We might be seeing these events already, classifying them as unusually powerful magnetar giant flares without knowing their true origin. The magnetic field of a strange magnetar might also evolve differently over time. In a neutron star, the magnetic field slowly decays as currents in the interior dissipate heat. But in a color superconductor, those currents could be persistent, almost eternal. The field might not decay in the same way. Instead, it could remain locked at near peak strength for millions of years, or it could undergo sudden, dramatic reconfigurations as the superconducting fluid inside settles into a new stable state. This could explain magnetars that show abrupt changes in their spin-down rate, a sign of a shifting magnetic field, for reasons that neutron star models struggle to account for. The ultimate signature, however, might be in the light they emit. The surface of a strange magnetar, whether it is a bare quark surface or a thin, magnetically confined crust, would be heated by the decay of its monstrous field in a unique way. The spectrum of X-rays and gamma rays coming from it could carry subtle fingerprint-specific ratios of high-energy photons that reveal the presence of quark matter below. Our telescopes are now sensitive enough to start looking for these spectral whispers. Each anomalous outburst from a known magnetar is not just a cosmic catastrophe. It is a potential message, a clue written in radiation about what lies crushed and perfect at its heart. Everything we have described, from density to magnetism, hinges on a single, deceptively simple mathematical relationship. At the heart of this cosmic detective story lies a concept called the equation of state. In essence, it is the universe's answer to a very basic question: how much can you squeeze something before it pushes back? For ordinary gases, the answer is straightforward: increase the pressure, and the volume decreases predictably. But inside a dying star, matter is pushed to limits where the rules of chemistry and atomic physics dissolve. The equation of state for such exotic matter is not a simple law, it is a fierce debate written in calculus. It defines the precise relationship between the crushing pressure in a star's core and the mind-bending density that results. This relationship is everything. It dictates the maximum possible mass a compact object can have before it collapses into a black hole. It determines how large or small a star of a given mass can be. It is ultimately the blueprint that tells us what a star is made of. For neutron stars, the equation of state is governed by the complex nuclear forces between neutrons, forces we are still struggling to understand from experiments here on Earth. This creates what physicists call a stiff equation of state. Imagine a very stiff spring in a mattress. You can put a lot of weight on it, and it will compress only a little, pushing back with tremendous force. A stiff equation of state means the matter resists being squeezed further, allowing the star to support more mass and remain relatively large, perhaps up to 20 kilometers across. Now consider strange quark matter. The pressure inside a quark star comes from a different source, the degeneracy pressure of free quarks, which behave more like a relativistic gas. This leads to a softer equation of state. Think of a much softer spring. For the same amount of weight, it compresses much more easily. A softer equation of state means that for a given central pressure, the matter can be squeezed to a higher density. This allows a strange star to pack the same mass as a neutron star into a significantly smaller, more compact radius. That 6-kilometer measurement from the Chandra telescope, the one that first sparked the strange star hypothesis, was a direct challenge to the equations of state. A star with that mass and that tiny size simply could not exist according to the stiffest neutron star models. It demanded a softer blueprint, one that allowed for greater compression. The equation of state is the master key. Every time we measure the mass and radius of a pulsar, through painstaking observations of how its gravity bends light from a companion star or how hot spots on its surface emit X-rays, we are taking a measurement of the universe's most extreme mattress springs. We are testing those blueprints. A growing catalog of such measurements is slowly painting a picture. Some neutron stars are indeed large and supportive of stiff equations of state. But others are perplexingly compact, hovering at the lower edge of what seems possible. These outliers are the most tantalizing. They are the objects that might require us to throw out the nuclear physics textbook and draft a new blueprint entirely, one written in the language of quarks. The ultimate goal is to find an object whose mass and radius sit in a region of the graph that no neutron star equation of state, no matter how stiff or soft, can reach. That lonely data point, isolated in a forbidden zone, would be the fingerprint of something stranger. It would be the signature of a star that is not just squeezed but fundamentally deconstructed. These theoretical blueprints are not drawn from thin air. They are forged in the silent, digital hearts of the world's most powerful supercomputers. Since we cannot recreate a dying star in a laboratory, scientists build one inside a machine. The tool for this impossible task is called lattice quantum chromodynamics. It is a way of simulating the maddeningly complex dance of quarks and gluons, the fundamental players of the strong force, by imposing order on chaos. The simulation begins by constructing a four-dimensional grid, a lattice of spacetime points. This is the stage. Onto this digital stage, the quarks are placed not as simple balls, but as probability fields that interact with each other through the gluons that hop between the lattice points. The supercomputer then calculates with staggering precision how every single component influences every other, over trillions upon trillions of virtual time steps. It is like simulating the exact motion of every molecule in a hurricane, but for a force infinitely more complex than wind. The goal is to see, in these calculations, how a soup of free quarks and gluons behaves as you dial up the density and lower the temperature, mimicking the final moments of a collapsing stellar core. Through this digital alchemy, physicists can watch as the chaotic quark-gluon plasma might, under the right conditions, crystallize into the ordered, superconducting state predicted for strange matter. They can test the equations of state, seeing how much pressure is needed to compress the quark soup to a specific density. These simulations are our only window into a process no instrument will ever directly witness. But this window is fogged with immense difficulty. The primary obstacle is known as the sign problem. In the complex mathematics of these simulations, certain calculations produce results that oscillate between positive and negative values. At the relatively low densities we can study in particle colliders, these positives and negatives mostly cancel out, giving a clear, stable answer. But as you push the simulation into the regime of a strange star's core, where densities are millions of times higher, the oscillations become wild and uncontrollable. The positives and negatives no longer cancel neatly, they drown the signal in digital noise. It is like trying to hear a whisper in the middle of a roaring stadium by averaging the crowd scream. The delicate information is lost. Overcoming the sign problem is one of the grand challenges in computational physics. Researchers attack it with clever approximations, new algorithms, and ever more raw computing power, slowly extending the simulations into the dense, cold territory where strange matter is born. Despite the fog, these virtual experiments are invaluable. They guide the entire search. From them, scientists extract predictions for the telltale signatures a real strange star would emit. They can calculate, for instance, how quickly such a star should cool via neutrino emission, leaving a specific thermal fingerprint in X-ray data. They can model the precise pattern of vibrations or oscillations that might ripple across its surface after a starquake, oscillations that could subtly modulate its X-ray pulse. They can even predict the exact spectrum of light that should come from a bare quark surface, a unique color of radiation never before seen. These predictions are then handed to the astronomers who scour the data from telescopes like Chandra, XMM Newton, and NICER looking for a match. It is a perfect feedback loop between the abstract and the observable. The supercomputer creates a digital ghost of a star that may or may not exist, and our telescopes search the darkness for its reflection. Every anomalous glitch, every oddly cold pulsar, every peculiar flare is compared against this library of digital prophecies. We are not searching blindly. We are hunting for a specific phantom, one whose shadow has been cast by the glow of 1,000,000 processing cores. That frozen droplet of quark matter is a time capsule. Its existence offers us a window not just into the death of a star, but into the very birth of the cosmos. The quark-gluon plasma that forms the heart of a strange star is not some exotic rarity. It is a direct echo of the universe's infancy. For the briefest moment after the Big Bang, before the first second had even ticked, the entire cosmos was a seething, unimaginably hot and dense soup of free quarks and gluons. There were no protons, no neutrons, no atoms, just a perfect primordial fluid of the universe's most basic ingredients. Then, as the universe expanded and cooled in those first microseconds, a profound phase transition occurred. The temperature dropped below a critical threshold. The strong force, which had been overcome by the immense thermal energy, finally took hold. Quarks and gluons, which had been roaming freely, suddenly found themselves bound together, forever confined into the protons and neutrons that would later build every atom in existence. This was the moment matter as we know it was born from the chaos. A strange star reverses this cosmic history on a local scale. Inside the crushing collapse of a massive star's core, gravity recreates those same conditions of immense density and pressure, forcing matter back into that primordial state. But here is the critical difference in the strange star. The collapse stops. The universe cooled and expanded, allowing quarks to bind. The strange star's own immense gravity provides a permanent external pressure that prevents expansion. Quark matter does not get a chance to cool into ordinary protons and neutrons. Instead, it freezes. It crystallizes into that stable, color-flavor-locked state. This means a strange star is not merely a dense object. It is a cosmic relic, a preserved sample of the universe as it was in its first fleeting instance. It is a fragment of time, a pocket of the Big Bang held in stasis by gravity's unrelenting grip. If we could ever study one directly, we would not just be studying a star, we would be conducting an archaeological dig into the first moments of reality. The conditions inside its core, the behavior of its quark-gluon plasma as it transitions to a superconductor, the very vibrations that ripple through its perfect fluid, all of these are clues. They are data points about the fundamental forces and phase transitions that shaped everything. Our particle colliders, like the Large Hadron Collider, can recreate the quark-gluon plasma for vanishingly small fractions of a second in collisions between heavy ions. We get a brilliant, fleeting flash of the early universe, but we can only study it as it instantly expands, cools, and fragments. A strange star, however, would be that same plasma held in perfect, permanent equilibrium. It is the difference between studying a single, brilliant spark from a firework and being handed a piece of the sun to examine at your leisure. By observing the properties of a confirmed strange star, its cooling rate, its oscillation modes, its neutrino emissions, we could test our theories of quantum chromodynamics under conditions no Earth-bound experiment will ever achieve. We could ask profound questions. Was the transition from the quark-gluon plasma to confined matter a sharp, sudden change or a smooth crossover? How did the first structures, the first protons and neutrons, actually condense out of that formless soup? The answers are locked inside these hypothetical objects. In this way, the search for strange stars beautifully bridges two seemingly distant fields, stellar astrophysics and cosmology. Astronomers hunting for a faint, cold pulsar with a peculiar glitch are, without realizing it, also hunting for a tangible piece of the universe's origin story. Every anomalous data point from a dense, compact object is not just a puzzle about a dead star. It is a potential message from the dawn of time, written in the language of quarks and gravity. Finding one would give us a laboratory for the Big Bang, a place where the most extreme laws of physics are not a fleeting memory, but a permanent, observable state. The impossible physics of a strange star could one day power our world. While we will never mine a droplet of that quark soup, the theoretical principles that govern it are already seeding revolutions in material science here on Earth. The dream of a room temperature superconductor, a material that conducts electricity with zero loss, has been a holy grail for over a century. Today's best superconductors require extreme cold, often hundreds of degrees below zero, making them impractical for widespread use. But the strange star offers a radical blueprint. Its interior is theorized to be a color superconductor, where quarks pair up and flow with perfect efficiency via the strong nuclear force, not electromagnetism. We cannot replicate that force in a lab, but studying the mathematical patterns of that pairing could reveal new pathways. It could inspire us to engineer novel materials, perhaps layered structures or exotic alloys, where electrons mimic that locked, coordinated dance at far more forgiving temperatures. Imagine power grids that transmit electricity across continents without losing a single watt, or maglev trains that glide silently on permanent currents, their efficiency unlocked by principles first dreamed up for a stellar corpse. This influence extends beyond mere conductivity. The quark matter inside a strange star is also theorized to be a nearly perfect fluid, a substance with almost zero internal friction. Understanding how such a state emerges from the chaos of individual particles is a frontier in hydrodynamics. Researchers are already creating tiny, fleeting versions of this perfect fluid in particle colliders by smashing heavy ions to create quark-gluon plasma. By studying how this primordial soup flows and thermalizes, scientists gain insights into the fundamental limits of fluid behavior. These insights could translate into advanced cooling systems for next-generation computer chips, where heat is the ultimate bottleneck, or lead to the design of novel lubricants that reduce friction in machinery to near zero, saving immense amounts of energy. The study of extreme matter is not an abstract exercise, it is a toolkit for innovation. When physicists chart the equations for a color superconductor, they are mapping a territory of ultimate efficiency. When they simulate a perfect fluid, they are exploring the boundaries of collective motion. These maps, drawn for a star, guide material scientists into uncharted regions of the periodic table and molecular design. The ultimate spin-off may lie in the realm of quantum computing. The bizarre, entangled state of quarks in a color superconductor represents a form of quantum order that is incredibly robust, maintained under immense pressure and density. Deciphering how this quantum coherence is protected from disruption could provide groundbreaking strategies for building qubits, the basic units of quantum information. Our current qubits are fragile, easily disturbed by the slightest noise from their environment. What if the secret to building a stable, scalable quantum computer was hidden in the way a strange star maintains perfect quantum order across an entire city-sized object? The research pathways opened by these cosmic mysteries are indirect but profound. We are not building starship engines from strange matter. We are reverse engineering the universe's own solutions to problems of stability, efficiency, and coherence. Each observation of a dense pulsar, each supercomputer simulation of quark pairing, adds another piece to a puzzle that spans from the first moments of the Big Bang to the future of our own technology. The value is in the questions themselves, for they force us to confront the limits of our knowledge and, in doing so, often show us a way through. The perfect stability of strange matter invites a darker line of thought, one that stretches from the heart of a star to the fate of entire civilizations. We have considered it as a cosmic artifact, but what if it became a tool or a weapon? This idea forces us to confront the Fermi paradox, the haunting question of why, in a galaxy so vast and old, we see no signs of other intelligent life. Could the answer be hidden in the physics of quark matter itself? Imagine an intelligence that has mastered not just atomic forces, but the deeper, more fundamental strong nuclear force. For such a civilization, strange matter would not be a distant curiosity. It would be the ultimate engineering material. A chunk of this substance, stable and indestructible, could serve as the perfect power source or reaction mass for interstellar travel. A starship's engine could, in theory, use controlled strange matter annihilation to release energy far beyond any chemical or nuclear reaction we know, propelling vessels across the gulfs between stars. But the same properties that make it ideal for propulsion also make it terrifyingly potent for destruction. A strange matter bomb is a chilling theoretical concept. It would not rely on fission or fusion, but on conversion. If a stable strangelet could be artificially created and then brought into contact with normal matter, it could theoretically initiate that catastrophic chain reaction, converting a planet or even a star into cold, inert quark matter. The detonation would be silent, a wave of transformation rather than fire, leaving behind only a growing sphere of perfect, dead stability. This is not merely science fiction. It is a logical endpoint of a technology that manipulates the building blocks of reality. If such a weapon is physically possible, then any civilization that discovers the secret of strange matter holds the power to sterilize solar systems. This introduces a grim solution to the Fermi paradox, the self-destruction hypothesis. Perhaps technological civilizations inevitably discover this ultimate power and, through accident or conflict, use it to erase themselves before they can ever announce their presence to the galaxy. The silence of the cosmos would then be the silence of a graveyard, littered with the cold, dark remnants of converted worlds. But there is another, even more unsettling possibility. What if the danger is not technological but natural? If strangelets are indeed created in the mergers of strange stars and then flung across the galaxy, they become cosmic bullets. A single, charged strangelet traveling at a significant fraction of light speed from an ancient collision could strike a planet like Earth. The impact energy alone would be catastrophic, but the real threat is the seed it might plant. If it is stable, it could sink to the planet's core and begin the slow, geological timescale conversion of the entire world from the inside out. This presents a natural filter for life. A galaxy where strange star mergers are common might be seeded with these indestructible hazards. Life that evolves on a planet could be utterly wiped out not by a supernova or asteroid, but by a silent, fundamental phase change long before it ever looks to the stars. In this scenario, the great filter, the hypothesized barrier that prevents life from becoming widespread and visible, is not a societal collapse or a war. It is a physical law. It is the universe itself possessing a latent danger in the stability of its own ingredients. Our own existence, then, might be a testament to an extraordinary run of luck, a quiet corner of the galaxy that has, so far, avoided these primordial landmines. Or perhaps it suggests that strange matter is not stable in the way we fear, that the chain reaction is a myth, and the cosmos is far friendlier to fragile, atomic-based life. The search for a strange star, therefore, is about more than stellar physics. It is a search for clues about our own cosmic context, and a silent answer to the question of whether the universe is ultimately built for construction or for silent, perfect erasure. The hunt for a star made of quarks requires listening to the universe with every sense we have. Our eyes, in the cosmic sense, are telescopes that collect light across the spectrum, from radio waves to gamma rays. But to find something so fundamentally alien, we must also learn to feel the vibrations of space-time and detect the ghostly passage of neutrinos. This combined approach is called multi-messenger astronomy, and it is our only hope for a definitive identification. Think of it as a detective assembling a case from disparate clues. A single piece of evidence can be misleading, but when fingerprints, witness testimony, and forensic data all point to the same suspect, you have a conviction. For a strange star, the conviction must be absolute. The investigation begins with a tremor in the fabric of reality. A gravitational wave observatory, like LIGO or Virgo, detects the characteristic chirp of two ultra-dense objects spiraling together. The signal's shape immediately tells us the masses of the objects. If they are too light to be black holes, they are neutrons, stars, or perhaps something stranger. The precise frequency and evolution of the gravitational waves encode information about their internal structure, their tidal deformability. A signal suggesting incredibly stiff, compact objects would be a red flag. This gravitational wave event is the starting pistol. It provides the exact time and a rough sky location for a cosmic catastrophe. Within seconds, an automated alert is sent to observatories around the world and in space. The hunt for light begins. Swift-moving satellites like NASA's a Swift or Fermi gamma-ray space telescope swing into position, searching for the flash of gamma rays that often accompanies such mergers. But the real scrutiny comes next. Larger, more sensitive X-ray telescopes like Chandra or XMM Newton stare at the location for days and weeks. They are not just looking for an explosion, they are performing a forensic analysis of the aftermath. Did the merger produce a black hole instantly, or did it leave behind a hot, massive remnant? This is where the strange star hypothesis faces its test. The newborn object, if it is a hypermassive neutron star or a strange star, will blaze with heat. Its cooling curve, the rate at which its X-ray emission fades, is a direct thermometer for its interior. A strange star with its color superconducting core is predicted to cool in a specific, slower manner than a neutron star. The X-ray spectrum holds another clue. As the hot surface radiates, the light carries the fingerprint of the atoms, or, in the case of a bare quark star, the lack thereof. Certain spectral lines from heavy elements would be absent on a perfect quark surface. The data streams in, a river of numbers and graphs. Meanwhile, radio telescopes join the vigil. If the remnant survives and begins to spin, it may become a pulsar. Facilities like the Very Large Array or the Future Square Kilometer Array would listen intently for its first pulses. Their focus would be on stability. Does this new pulsar exhibit the strange, frequent microglitches predicted for an object with a thin, brittle crust over a quark ocean? Or does its spin-down behave with an odd regularity, hinting at a magnetic field frozen into a superconducting interior? Each messenger brings a different piece of the puzzle. The gravitational waves tell us about the merger's mechanics and the object's stiffness. The X-rays tell us about the remnant's heat, composition, and size. The radio waves tell us about its magnetic personality and seismic activity. And on the horizon is another messenger, neutrinos. These nearly massless particles stream directly from the heart of the inferno, carrying untouched information about the nuclear and quark processes inside. A future neutrino observatory catching a burst from such an event could, in theory, distinguish between the neutrino signature of a neutron star and a quark star. A confirmed detection from all these channels, all pointing to the same bizarre conclusion, would be the scientific breakthrough of the century. It would transform a theoretical phantom into a catalogued celestial object. We are no longer waiting for a single lucky observation. We are building the network to conduct the interview, to ask the universe direct questions and understand its answers in a language of waves, particles, and light. The next chirp from the dark could be the one that starts the conversation. The universe rarely deals in pure forms. Between a perfect quark star and a conventional neutron star lies a fascinating middle ground, a cosmic chimera known as a hybrid star. This theoretical object is not a uniform droplet of strange matter. Instead, picture a layered sphere like a jawbreaker candy with a secret center. Its outer layers would be the familiar, crushing density of a neutron star, a thick mantle of neutrons packed together. But deep within its heart, under pressures that finally overcome nuclear forces, the neutrons dissolve. The core becomes a sphere of quark matter, likely in that color-flavor locked superconducting state. This creates an object with a split personality. Its surface properties, its glitches, and its magnetic field might look very much like a neutron star's. But its interior, its maximum possible mass, and its cooling behavior would be subtly different, governed by the exotic physics of its quark core. The transition boundary between the neutron mantle and the quark core would be a realm of staggering density gradients, a place where matter changes its fundamental nature over a span of perhaps only a few meters. Detecting a hybrid star is an even finer challenge than finding a pure strange star, as its external signals would be a confusing blend of two different sets of rules. An even more violent possibility is the quark nova. This is not the birth of a strange star from a supernova, but its delayed, explosive awakening. Imagine a neutron star that has existed for centuries, even millennia, spinning quietly in the dark. Inside its core, the pressure is immense, but perhaps just below the threshold needed to break neutrons apart. Then, something tips the balance. It could be the slow accumulation of mass from a companion star, or a particularly violent starquake that momentarily increases the central density. The core pressure crosses the critical line. In a cascading, catastrophic phase transition, the neutron matter in the core suddenly shatters into free quarks. This conversion releases a tremendous burst of energy as the quarks rearrange into their more stable configuration. The result is a second, spectacular explosion from an already dead star. The quark nova would outshine the star's original supernova, blasting away its outer neutron star crust and ejecting a shell of material rich in heavy elements. For observers, it would appear as a sudden, incredibly luminous flash of gamma rays and light from a known neutron star, a star seemingly coming back to life to die a second, stranger death. This model solves several puzzles, like the origin of certain heavy elements and some unusually bright supernova remnants that seem to have too much energy for a single explosion. These competing models enrich the theoretical landscape but turn the observational search into a masterclass in cosmic forensics. We are no longer simply looking for one type of phantom. We are trying to distinguish between a pure strange star, a hybrid star, a quark nova remnant, and an unusual neutron star. Each leaves a slightly different set of fingerprints. A hybrid star's glitches might be less severe than a neutron star's, as its quark core is more fluid and might dampen crust movements. A quark nova remnant would be surrounded by a very specific shell of debris, with a chemical signature hinting at a sudden quark conversion event. The cooling curves, the vibration frequencies, the exact shape of the gravitational wave signal from a merger, all these data points must be weighed against a growing library of theoretical predictions. This complexity is not a barrier to discovery, it is the very path to it. Every new observation of a dense stellar corpse, every anomalous piece of data, is fed back into the supercomputer simulations. Theorists adjust their models of the quark matter equation of state, the thickness of the hybrid star transition layer, the energy of a quark nova. They generate new predictions for what to look for. This iterative dance between theory and observation is how we map the unknown. The goal is not just to find an object that is weird, but to find one whose particular flavor of weirdness matches only one specific predicted recipe. The existence of competitors makes the eventual discovery far more compelling, because it means we will have truly understood what we are seeing, not just stumbled upon a mystery. The strange star is not hiding alone in the dark. It is part of a family of theoretical possibilities, each waiting for its moment to step into the light of our data. Theoretical physics rarely stays confined to journals and equations. It bleeds into our stories, becoming the bedrock for new myths. For decades, the concept of strange matter has been a fertile seed for science fiction, a way to give tangible, often terrifying, form to the universe's deepest mysteries. In the novels of Alastair Reynolds, strange matter is not just a curiosity, it is a plot device of cosmic scale. His Revelation space universe features the Hell-class weapons, projectiles made of programmable strange matter that can eat through planets and stars, converting them into more of itself. This dramatizes the doomsday hypothesis we discussed, turning an abstract chain reaction into a narrative engine for apocalyptic stakes. It is a perfect example of how science fiction extrapolates, taking a fringe theoretical possibility and asking, what would this mean for a civilization that could wield it? The drama is not in the equations but in the consequences, making the physics feel immediate and visceral. Video games provide an even more interactive canvas. In the grand strategy game Stellaris, players can encounter strange matter as a rare and powerful resource. It is described as a substance that defies known physics, and it can be used to construct advanced technologies like shields or weapons that are far beyond ordinary materials. Here, the concept is gamified. It becomes a prize, a symbol of technological mastery over the fundamental forces. By making strange matter a coveted resource, the game teaches players on an intuitive level that controlling the building blocks of reality is the ultimate power. These portrayals are never perfectly accurate, and they should not be. Their purpose is not to deliver a lecture on quantum chromodynamics, but to evoke a sense of wonder and scale. They translate dense mathematical concepts into narratives of exploration, conflict, and discovery. When a character in a story worries about a strange-alert infection, or an empire in a game harvests quark matter from a dead star, these ideas cease to be abstractions. They become part of a shared cultural vocabulary. This is profoundly important for science itself. Many working physicists and engineers today cite science fiction as their first spark, the thing that made them look up at the night sky and ask how any of it could be possible. A dramatic portrayal of a quark star in a film or a novel is a gateway. It prompts a curious viewer or reader to search for the real science behind the fiction, leading them down a rabbit hole of research papers, documentaries, and articles. In this way, science fiction acts as a vital translator and amplifier. It takes the cold, complex output of theoretical models and wraps it in human stories of ambition, fear, and curiosity. It reminds us that these are not just puzzles for academics, they are questions about the nature of reality that belong to everyone. The next great mind to finally prove or disprove the existence of a strange star might be sitting in a classroom right now, their imagination first set alight not by a textbook, but by a video game or a paperback novel that dared to make the universe's strangest possibilities feel real. The silence of these cosmic relics may soon be broken by a new generation of eyes and ears. Our hunt for a star made of quarks is about to accelerate, powered by observatories so advanced they feel like science fiction made real. The James Webb Space Telescope, already revolutionizing our view of the earliest galaxies, holds a quieter promise for stellar forensics. While it peers into the infrared, it can detect the faint, residual heat of ancient, cold, compact objects. A mature, strange star, having cooled over millions of years, would glow not in brilliant X-rays but in the dim infrared. Webb's unparalleled sensitivity could pick out these cold, dark orbs from the background clutter of space, identifying candidates so faint they were previously invisible. It would be like finding a cooled ember in a field of ash, a subtle thermal whisper hinting at a perfect cold heart. But to understand what that heart is made of, we need to dissect its light with surgical precision. This is the mission of Athena, the Advanced Telescope for High-Energy Astrophysics, a European Space Agency project slated for the 2030s. Athena will be an X-ray observatory of unprecedented power, with a mirror so large and instruments so sharp it will perform high-resolution spectroscopy on the surfaces of pulsars and magnetars. Imagine not just seeing a point of X-ray light, but being able to read its detailed chemical fingerprint. Athena could analyze the spectrum of a suspected strange star's emission, searching for the telltale absence of atomic spectral lines that would betray a bare quark surface. It could measure the temperature variations across that surface with exquisite detail, testing predictions of how a quark ocean should cool. Where current telescopes see a blur, Athena will see a forensic report. On the ground, a colossal ear is being built to listen to the universe's most precise clocks. The Square Kilometer Array, or SKA, is not a single dish but a vast network of thousands of radio antennas spread across South Africa and Australia. When complete, it will form the most sensitive radio telescope in history. Its core mission includes pulsar timing on a scale we can barely comprehend. The SKA will monitor thousands of pulsars simultaneously, tracking the regularity of their spins with nanosecond precision. It is designed to catch the subtlest of glitches, the tiniest wobbles, the most minute variations in spin down that could reveal the internal structure of these dense stars. For the strange star hunt, it is the ultimate glitch detector. If a pulsar exhibits a pattern of microquakes or a magnetic personality that defies all neutron star models, the SKA will hear it. It will turn the statistical search for an outlier into a systematic census, allowing scientists to find the one bell ringing in a universe of drums. This is not a distant dream, it is an unfolding reality you can follow. The data from these missions will flood into public archives, analyzed by teams around the world and by citizen scientists. The mystery of the strange star is a living, breathing scientific question, one that will have new chapters written in the coming decade. When Webb identifies a peculiarly cold point of infrared light, when Athena takes its first high-resolution spectrum of a magnetar, when the SKA logs its first anomalous pulsar glitch, the headlines will be made. You'll be able to watch in real time as the pieces of this cosmic puzzle either click into place or scatter, forcing theorists back to their drawing boards. The hunt is on, and the tools for the final verdict are already being built, pointing toward the dark, waiting to catch the first clear glimpse of a universe built from a different recipe. The power to create new states of matter carries a profound responsibility. We have explored the cosmic potential of strange matter, but what about our own attempts to summon its shadow here on Earth? The world's largest particle collider, the Large Hadron Collider, smashes lead nuclei together at nearly the speed of light. For a fleeting instant in a space smaller than an atom, it recreates the quark-gluon plasma of the early universe. Could such an experiment, in theory, create a stable strangelet? And if it did, could that microscopic speck trigger the catastrophic chain reaction we fear? This is not a plot from a movie. It is a serious ethical question that was rigorously examined before the collider ever powered on. Independent safety reviews were conducted, bringing together experts in particle physics, astrophysics, and risk analysis. Their conclusion was unanimous and firm. The conditions in the collider, while extreme, are fundamentally different from the dense, cold, high-pressure environment inside a collapsing star. The mini fireballs created are incredibly hot and expand almost instantly, making the formation of a cold, stable droplet of strange matter fantastically unlikely. Furthermore, nature has been running its own far more powerful experiments for billions of years. Cosmic rays, particles from deep space with energies far exceeding anything our colliders can produce, have been bombarding celestial bodies like the moon and neutron stars. If stable strangelets were easily created, these natural laboratories would have produced them, and we would see evidence of their destructive conversion. We do not. The cosmos remains full of normal matter, a strong argument that the doomsday scenario is not just unlikely but physically implausible. Yet, the ethical framework behind this reassurance is as important as the physics. How do we decide it is safe to probe the unknown? The process relies on a principle of natural precedent. We look to the universe as our guide. If a process does not occur naturally under conditions we can observe and understand, then we can proceed with a high degree of confidence that our scaled-down experiments are safe. This framework allowed us to build the collider and discover the Higgs boson, expanding our knowledge of reality. But it also establishes a critical boundary for future exploration. As we contemplate even more powerful machines or experiments with entirely novel forms of energy, this ethical litmus test must be applied anew each time. The deeper question is philosophical. Humanity's drive to understand the fundamental forces is what defines our progress. It is a beautiful, restless curiosity. But with each new layer of reality we peel back, we potentially gain access to levers of unimaginable power. The story of strange matter is a parable for this journey. It shows us that the universe's building blocks can assemble in ways more stable and potent than anything in our ordinary experience. Our responsibility is to walk that line with immense care, letting the natural cosmos be our safety manual, while never ceasing to wonder what perfect, and perhaps perilous, recipes are written into the fabric of everything. The moment the data confirms a strange star will be a shockwave through human understanding. It will begin not with a public announcement, but in a hushed room where a graph on a screen defies every known model. A quiet, collective realization will dawn among the researchers, followed by a frantic, joyous scramble to verify, to triple-check, to rule out every other possibility. When the certainty settles, the world will change. Nobel Prizes will be assured, but that will be the least of it. Every textbook chapter on stellar evolution, from high school to graduate level, will require a new page. That single confirmed data point will carve a permanent niche in the cosmic bestiary, right between neutron stars and black holes. The paradigm of what matter can be will have shifted under our feet. This discovery would do far more than just add a new entry to the catalogue of celestial objects. It would provide the first direct, unassailable proof that matter can exist in a stable state beyond the atomic nucleus. We have theorized about quark-gluon plasmas and color superconductivity, but a strange star would be a permanent, observable specimen. It would become the ultimate laboratory for quantum chromodynamics, the theory of the strong force. By studying its cooling, its vibrations, its neutrino emissions, we could test our most fundamental theories under conditions no Earth-bound collider can ever sustain. We would be probing the rules of the universe in a natural, billion-year-old experiment. The ripple effects would force a dramatic re-evaluation of stellar life cycles. How many of the dense objects we have already catalogued as neutron stars are actually strange stars or hybrid stars? Our models of supernova would need revision to account for this new possible endpoint. The very history of our galaxy, written in the remnants of dead stars, would need to be reread with this new understanding. It would answer old questions and ignite 100 new ones, driving decades of fresh observation and theoretical work. Ultimately, such a discovery would stand as a towering monument to human curiosity. It would affirm that by building tools to listen to gravity and see in X-rays, by daring to simulate the birth of the universe in silicon, and by relentlessly questioning the nature of reality, we can uncover truths hidden in the deepest dark. Finding a strange star would be a message from the cosmos itself, a reminder that the universe is stranger, more varied, and more wonderfully inventive than we ever dared to assume. From the smallest Lego bricks of reality to city-sized spheres of perfect fluid, this journey has taken us to the edge of what matter can be. We began with the humble up and down quarks that build our world, then followed gravity's crushing power into the heart of a dying star, where those familiar particles shatter and recombine with their strange sibling. We have explored cosmic monsters that are not balls of fire, but single droplets of a primordial recipe, Objects so dense they weigh more than mountains in a teaspoon and so stable they could outlast time itself. This is not merely astronomy, it is a detective story written across the fabric of space-time, using gravitational waves, X-ray whispers, and the silent ticks of pulsar clocks as clues. The search for a strange star lies precisely where the most thrilling science always resides, at the vibrant, chaotic intersection of bold theory, meticulous observation, and boundless human imagination. It requires us to trust the mathematics that predicts a color superconductor inside a collapsing core, then to build machines delicate enough to hear the faintest tremor from a merger a billion light-years away. It is a testament to our species' unique drive to look into the darkness and not just wonder, but to listen, to calculate, and to ask. So as new telescopes peer deeper and new algorithms sift through the noise, remember that you are witnessing this search in real time. The cosmos is under no obligation to be simple or familiar. Its greatest secrets are often hidden in plain sight, masquerading as a faint point of light or a puzzling blip in the data. Stay curious, follow the discoveries as they unfold, for somewhere in the vast dark between the stars, a perfect sphere of the early universe may be waiting, a silent monument to a reality far stranger and far more wonderful than we ever dreamed.